A little bit smaller class today. Thank you all for being here in person. Today's topic is instance centers. For those of you who attended the tutorial this morning with Robin, that was his last tutorial for the course. Yeah, I think Robin was doing a great job. I heard from a few of you as well about that. He had a lot of energy for discussing some creative example problems and whatnot. Each month of the course we have a different tutorial TA. I've sort of developed that method of doing the course, so the TA was attending all of those lectures, and the next TA is named Taha. Are you here, Taha? No, he's not here today. He'll start coming to lectures next week, and he's going to lead the session starting next Friday. Anyways, for those of you who are in tutorial this morning, Robin covered basically how to find instance centers. I'm going to do one example problem for you today, finding instance centers. I'm not going to do a lot more in lecture. There's one technique for finding instance centers, which Robin used in tutorial today, and that's called Kennedy's theorem. It's a pretty simple idea. It turns out to be the best way of finding instance centers. We'll use that today. So that'll be a review for those of you who are in tutorial this morning. I suggest after today's lecture you give a try to the problem set, which is posted on instance centers. The first, I think, two problems, the first half of the problem set is about finding instance centers. Give those a try now. If you didn't attend the tutorial and you're not sure what to do, check out the video that Robin made from today. It'll be a nice follow-up from what I do in class today. Okay, just a reminder, we have a photographer today. I didn't hear from anyone about not being in the photo, so you could be in her photos a little bit. And proposals to do next week. Any other questions about the course material? Yeah?
The problem set due next week or the week after?
The problem set's on instance centers. It's on finding them, which we're going to finish today, and on using instance centers, which we're just starting today. I forget the deadline that I put on it. It's at least a week from when I posted it 2 days ago. I don't recall the deadline. Anyone remember the deadline? Instance centers, yeah.
Sorry, no, I don't think the problem set's posted yet.
Oh, it's not posted. Okay, we'll check it out. Problem set on instance centers will be posted soon. But I haven't taught you. I'll finish covering the material for instance centers, not today, but in the next lecture, which is going to be Tuesday. So I'll make sure the deadline is reasonable for you to complete it after that. After today, you'll be able to do the first half, so check it out. I'll post it after lecture today. Sorry about that. Any other questions? Thanks for pointing that out. Okay, so today, in finding instance centers with an example, and then we're going to do, our main topic for today is going to be using instance centers, ICs, for velocity analysis. So we're going to use them to find the input to output relationship in our mechanisms. So given some crank speed, calculate the speed of a slider on the other side of the mechanism. We're going to do those examples today. Okay, so the last technique, I gave you some techniques in lecture for finding instance centers. The first was using kinematic pairs. The second was drawing some two velocity vectors. And our third method for finding instance centers is called Kennedy's theorem. And so this is kind of a strange thing. If you plot out a bunch of instance centers for real mechanisms, you'll see that this is always true. Take any three links on your mechanism. Doesn't matter what they are. Any three links, I, J, and K, those are the numbers of the links. Their instance centers will lie along a line. And so those instance centers are going to be, it's just every combination of I, J, and K. So Pij, Pik, and the third one would be Pjk. Okay, so those are the three instance centers affiliated with those three links. You may say, what about Pji? Remember, that's the same as Ij. Right? The order of the subscripts doesn't matter. So that one's already accounted for. So those are the three instance centers associated with those three links. Okay, so you can choose any three links. And this is going to be a really powerful practical tool for finding those instance centers, which we're going to use for velocity analysis. Okay, so You'll need to memorize this, but after doing a few examples and doing the problem set, you'll be able to remember it pretty easily. Okay, so the problem we're going to do today is called an inverted slider crank. So I'm going to use this Kennedy's rule for you by example. We're going to do this example problem. I'm going to draw this mechanism for you. Try and draw it as close to mine as you can, because if you make a little difference, it'll put some of the instance centers off the page. So we're going to have two base pivots. Let me get the geometry right. So two base pivots, and there's going to be an output link here with a slider on it connected over here. So we call this an inverted slider crank because it has all the same links as a slider crank, but in this case, the ground link is a different link. So we've kind of tilted the whole thing up, and now the slider is free to rotate. So we'll just label these 2, 3, and 4. Okay, I think it's different numbers than we used before, because I still want to keep the ground as link number 1. So this is our slider crank inverted version. And what we're going to do here is we're going to find all of those instance centers. That's our task here, is to find all of the instance centers. And we're going to put them on our page here. Some will be off to the left, just so you can plan your notes here. And we're going to ask ourselves, the last thing I did in lecture last time was, how many instance centers are there? And we said that's equal to n times n minus 1 over 2. So that's going to be, there's 4 links. So 4 times 3 divided by 2 gives us 6. 4 times 3, yeah, 12 over 2 is 6. So there's 6 instance centers. And what I suggest when you're finding instance centers is write out all of them so you can keep track. Because it's easy to kind of get messed up with trying to just keep track of all these. So I'm just going to make a list of all the combinations of 1, 2, 3, 4. So the ground has an instance center with each of the links. And those are the points about which each of our links rotates. You remember that was the main concept in last lecture, yesterday. Link 2 rotates about P1, 2. And that one's an easy one to find. Rotates about that point. Okay, so that's our first 3. Next 3, I'll just go through all the other combos. P2, 3. P2, 4. So that's 5 of them. And there's one more. What's the one that I'm missing here? 2, 4, 3, 4, right? Okay, and you can switch those subscripts. It doesn't change what they mean. So those are the 6 that we need to find. And so we're going to use the methods at our disposal. First, let's use our kinematic pairs. Those are the really easy ones to find. So if you're not recalling, check back to last lecture where we looked at each type of kinematic pair. Turning pairs are the easiest. So at those points, right, link 3 and link 1 are connected here. The microphone is, my booming stopped. I'll just check it out. Perhaps the mic died, in which case the battery died. We'll see if it stays on. Okay, so that's P1, 3, where link 1 and 3 have a common velocity. And that velocity happens to be 0, because one of those links is link 1. So link 3 rotates around P1, 3. Link 2 rotates about P1, 2. And P1, 4 we can't find directly, right? It's not pivoting around the ground. But we can look at our other kinematic pairs. There's a turning pair right here connecting link 2 and link 4. So we can have, I think it went out again. A weird sensation. So right here at this turning pair, we can see that's where our, what's that going to be? 2 and 4. So that's just P2, 4 right at that turning pair there. Okay, the remaining, I'll take your question in a second. The remaining kinematic pair is the slide. That's 4 sliding on 3. So that's a sliding pair. And you recall sliding pairs are often infinity. In the example I did before, it's up, down, because the slide was horizontal. But we just need to find the sliding axis and go perpendicular. So off here somewhere, off at infinity is 3, 4. Okay, P34 is off at infinity somewhere, but we don't know where to draw that line necessarily. We don't know where to put this line, so we're just going to put it there for now. It's just a direction, really. And later when we solve the rest of the problem, we're going to see where that line should go. Okay, so it's perpendicular to the slide off in that direction. Any questions about this? There was one up here. Somewhere. Answered it. Okay, very good. So these are our easy ones. These are the easy kinematic pairs. So we're going to use Kennedy's theorem to find the remainders if we can. And that's probably my suggestion when doing instance center search. Start with kinematic pairs. Next, try Kennedy's theorem. Because once you do it once, you'll be able to deploy it pretty quickly. Okay, so let's see which ones we want to find. Let's find P14 next. P14. And that's a nice instance center because that's the point about which link 4 is rotating. Okay, so if we can find that one, that's a nice way of visualizing the motion of link 4. And that it's true because 1 is part of this one. So it's P14. So it's like a point on link 4 where the velocity is 0. We'll think about that again once we find it. Okay, so Kennedy's theorem is going to allow us to find P14 by basically finding two lines. So we're going to say, okay, what sets of 3 can we write for this? And we're going to try and write 2 sets of 3. So the board keeps lining up. We're going to have 2 sets of 3. So P14, we're going to have 2 sets of 3 and try and triangulate some position somewhere. Okay, so basically we can just choose another link to be I, j, and k. So let's say I and j are 1 and 4. K can be link 2, let's say. So that would be P12, P24. So that's like k equals 2. Okay, and the only other combo you could choose is k equals 3. That's the only other link in our mechanism. So that would be the other one you could choose. P13 and P43. Or I'll call it 3-4. Same thing. Okay, so we know from our definition of Kennedy's theorem that P14 should lie along both of these lines. So if we know where these points are, we're going to be able to find our unknown. So P14, that's our unknown. Let's just see which ones we already know. P12, that's at the base of link 2. I'll just put a check mark. And P24, that's up at the turning pair here. So that first line we know. So P14 needs to lie on a line connecting those two. And we could draw that. You can do, I suggest if you're doing these, maybe use a light pencil line to put these on. So here's those 2 points. So somewhere along that line should be P14. P14 should be on this line somewhere. Okay, but it's also along a second line, and that's going to allow us to triangulate the position. Okay, so let's see, do we know these ones? P13 is right here. We know that one. And P34. P34 is a weird one, right? So the question is, we know that one for sure, check mark. P34 we kind of know. We know its direction. So the question is, can you draw a line connecting P13 and P34? And yeah, we know the direction, right? P34 tells us the direction. So if I wanted to draw that line intersecting with P13, I could do that. So it should be parallel to the slide, parallel to this line, which is perpendicular to the slide, and intersecting here. So let me put that on. It's like I'm shifting this P34 line down to intersect with P13. Okay, so P14 should also be on that line. So I put 2 dotted lines, each corresponding to one of these instance center triplets. Okay, and they intersect down here. You notice I had to curve up a little bit because I went off the board, which is a common issue if you're solving problems on your own. Sometimes the instance centers will be off quite a distance, and you'll have to choose where your page ends properly. Well, let's say I found it correctly down here. This is going to be intersection of those lines, P1, 4, found by Kennedy's theorem. Okay, so Kennedy's theorem is a nice practical method. It's always going to look just like this. You're going to search for 2 lines where the intersection point would allow you to triangulate the position. Any questions about this one? And Robin was solving some other problems with these methods this morning. Okay, the remaining one is P24, right? P24, no. What's the remaining one that we haven't found yet? 2,3. P23. So we can do the same thing. Let's try it by Kennedy's theorem. So we're going to have 2 triplets. So let me choose K. So I equals 2, J equals 3, K could equal 1, or K could equal 4. That's the only other choices. So if K equals 1, we'd get 1, 2, and 1, 3. And K equals 4, we'd get 2, 4, and 3, 4. Okay, and I may not be following the exact order of these that Kennedy's theorem said. It's just the combinations of I, J, and K to make these triplets. So P23 needs to lie on both of these lines. So we'll do the identical process. That's the one we're looking for, P23. We know where everything else is, right? We know where every other instance center is, so we know this is gonna work for us. Let's do the first one. 1, 2, and 1, 3. Those are our base pivot points. So that one's easy enough. Okay, so we'll say P23 should be on this dotted line somewhere. That's our first line. Second line, so we can triangulate, is 2, 4, which we know is right in the center, and 3, 4, which is that direction. So this gets a little weird, I think, that the second one, we're going to draw a line connecting P24 to P34. Okay, P34 is a direction, and it needs to go through P24. So we can put it on there. The weird thing is that when we found P14, we acted like P34 was down here. But now we're acting like it's up here. It's really just a direction. So we'll put the vector on there like that, but we'll keep in mind it's just a direction, and we can put it wherever we want, and it can lie on multiple different lines. Okay, at any rate, we found the 2 line intersection down here. That's our last instance center, P23. So that's where link 2 and link 3 share the same velocity. Any questions about our search process? Yeah.
So K is just the subscript aggregator?
Yeah, so Kennedy's theorem, we had I, choose 3 links, I, J, and K, and write all the combos that consist of I, J, and K. So I already know 2 of them need to be, like I'm searching for P23. So I say I is 2, J is 3, and K is something else. And there's only 2 choices. In this case, 1 and 4. If you have a mechanism with more than 4 links, you could make more triplets. If you had a mechanism with 6 links, you come up with a whole bunch of triplets. And they would all triangulate to the same spot, which gives you multiple solution methods. Another question in the back.
I
P24, yeah.
Classified it as a turning pair, but it's also sliding.
So P24, yeah, your question was, is it a turning pair, but it looks like it's sliding as well. P24 is the connection between link 2 and 4, which is a turning pair. So yeah, turning pair. But there's also sliding going on in this area. That has to do with 3 and 4. That's a separate kinematic pair, 3 and 4. So those happen at the same location here, but there's two different kinematic pairs. Turning connects 2 and 4, sliding connects 3 and 4. Any other questions about this? Yeah?
I was just going to say, so in the example we did this morning, there was like 15 infinite data centers. So how should we like stay a little bit organized? Because I feel like there's so many lines that are around.
Yeah, it's crazy. You say 15 was what you were looking for this morning, right? Just a few more links, it grows, right? Our equation is n times n minus 1 over 2. That's how many we have, right? So they grow quickly. You see my board is already getting a big mess. How do you keep track of the page and keep it from getting cluttered is your question. It's a great question. When I solve them twice. I do once as a sketch with pencil, and it becomes a mess. But I don't do things very accurately. Then I redraw it, nice and accurate, and I put only the important things on. So there's no magical method. That's my biggest suggestion to you. On an exam, I'm going to probably give you a starter mechanism to work with. And they take a while, right? The more complicated they are, it takes a while to hunt everything down. So probably on an exam, I'm not going to give you something that requires you to draw 50 lines on one page. Yeah. Other questions? Okay, so this is finding instance centers. And this is all I'm going to say about finding instance centers. These are your methods. We're not done for today. We're going to use instance centers, which I think is the fun part. So if you want to see more examples of finding, the textbook does a bunch of examples. So check those out and check out the tutorial if you didn't watch it, if you weren't there this morning. Okay, so finding instance centers. This is going to be our first velocity analysis method. And we're going to learn 3 different velocity analysis methods in the course. Okay, so our method is going to be, we're going to use instance centers like Pij, connecting 2 links. And we're going to use that to transfer velocity between links. Okay, and I put transfer in quotes, and we'll see what that really means. But basically, our goal for velocity analysis is going to be something like, we're going to study this exact problem right here. This inverted slider crank. A goal could be, given our input speed, theta 2 dot, rotation rate of link 2, let's say it's rotating clockwise at 1 radian per second. Okay, so link 2 is going clockwise at 1 radian per second. Let's find the output rotation rate of link 3. That's a typical analysis problem. Okay, and so we're going to use our instance centers, which tell us something about the velocity relationship between links. And up till now, it's been a little bit abstract. But right now, we're going to see how that is going to be used practically. So let's think about the meaning of our instance center. So for this problem, we want to go from link 2 to link 3. So we're going to use P23 to do that. So let's write out what the meaning of P23 is to remind ourselves. This is the point where both of those links, 2 and 3, have the same velocity. Right? So that's how we're going to transfer them. And you'll see how this works. And the way we're going to write this is we're going to write out the velocity of that point P23. And we're going to sort of assume first, we're going to assume it's on link 2. And then we're going to say that's the same as the velocity of P23 on link 3. So this is and these are vectors. Although you'll see later, we're just actually going to work with scalars. But this is the core of our solution process. And so these are going to be two problems or two equations we're going to write out, and we're going to set them equal to each other. So first we're going to study link 2, then we're going to study link 3. Okay, so what we're going to do next is we're going to draw link 2 off by itself. And we're going to put P23 as well. Okay, so I covered up our mechanism, but link 2, make sure you need space off to the left because P23 is off to the left. Link 2 looked like that, right? With P23 was out here. Okay, P23 was well off to the left. So this is our process. I'm going to bring my drawing back, cover up our process. Okay, here's our drawing. P23 was off to the left. Let me move it a little closer, similar to my drawing there. Okay. So our goal here is to write out velocity of P23, right? And we're assuming it's on link 2. That's what we're going to do. So the thought process that I like to follow, and I did this in the last 2 lectures, is let's glue a piece of paper onto link 2. Just extend link 2. This is just a thought experiment. So let's extend it. I drew that as a dotted line. So let's extend it so that it includes P23. Okay, if we think about our definition, P23 is the point on link 2 where we have a velocity that's of interest. Okay, and if we do it like this, we know the velocity direction needs to be perpendicular to this line, right? It's rotating about this point. Right, the whole length's rotating. We said it's clockwise. So we know the velocity of that point. We call that a case 1 situation, right? Our point of interest, P23, and this ground point are on the same link, so the velocity must be perpendicular. Okay, and what's the magnitude of that? We need to know that distance, right? So in general terms, we would say this link 2, it's rotating around a key point called P12. Right, so every link is rotating around this point, P1, and then whatever the link is. In this case, the link's 2. Okay, so we wrote out, we call it case 1, 2 points on the same link. And we need to know this distance times the rotation rate. That gives us our velocity, right? So the distance we're going to write as r, and we're going to use those 2 instant centers to sort of denote our distance. So the distance is between P12 and P23. That's sort of that moment arm there. And the rotation rate is going to be theta 2 dot. Rotation rate of our link of interest, link 2. Okay, and this is all there is to it. This is our analysis for link 2. And we call that part 1 of our solution method. That's velocity of P23 acting like it's on link 2. Okay, so that's acting like it's on link 2. Next, let's repeat that process, acting like it's on link 3. So we're going to draw the same thing, but for link 3. And we're going to extend link 3 in our minds to cover our point. Let me get my drawing right. I need just one more chalkboard here. Okay, so here's our point, P23 over there. here's our link 3. Okay, there's link 3, just isolated by itself. Our point of interest is P23 over here. So we're going to do the same thing. We want to write out velocity of P23. Okay, and this time we're writing it like it's on this link 3. So let's extend our link 3 in our minds. Let's extend it to include P23 and say, okay, what's the velocity of that point? It's basically the same drawing as I had above, right? So we'd say, okay, let's connect this base point. If we want to find velocity of that point, P23, it's going to be perpendicular to this line. And that line connects P13. P13 is the point about which link 3 rotates, and our point of interest. And so we know the velocity needs to be perpendicular to that. And we'd say, should it be up or down, the velocity? Just looking at our mechanism, it's a little hard to tell. Is link 3 rotating clockwise or counterclockwise? 2 is going clockwise. It's hard to tell. It depends on the exact geometry. But think about our main equation. Our main equation of interest is that the velocity is the same for both of our cases. Here's link 2, here's link 3. On link 2, the velocity of P23 was up. So it's got to be the same here. Also up. Okay, and it's not by chance that that is perpendicular to this line. Right? That's why P23 is there. Because on both link 2 and link 3, the velocity is vertical in the upward direction. Okay, so we can write that out as an equation now. We have these points of interest, so it's going to look just like this equation up here. This is going to be our number 2, though. So basically, everywhere we had a 2, we're going to replace that with a 3 here. Okay, so this is our expression. That's the distance between those 2 points multiplied by the rotation rate of this link, which is link 3. Okay, so this is 2 ways of finding the velocity of our point of interest, P23. That's our transfer point. And we're using that transfer point to convert between theta 2 and theta 3. So the last thing that we're going to do is just that. Let's assemble our final thing, which is equation 1 equals equation 2. We'll just set them equal to each other. So I'm just going to rewrite them here. Okay, so that's equation 1 equals equation 2. And now we have what we want. We have a relationship between theta 2 and theta 3. And we can calculate it. We can solve for theta 3 dot. That's our output rotation rate. So just divide by this r here. Okay, and we get our final solution. So we have a ratio of lengths, and you can measure those on your diagram. So this is going to be a scaled, dimensional, graphical process. You measure these lengths and multiply it by your input. So let's calculate it. Let's make up some reasonable lengths for our links. Let me say that Again, our diagram is hidden here. So everything is similar lengths. Let me say 2 and 3 centimeters for those. Let me just write them out here. Let's say I measured those. So P12, P23. That's this length here. Let's say I measured that on my diagram to be 2 centimeters. And the next one, P1323. Let's say I measured that to be 3 centimeters. And then we multiply that by our rotation rate, which was part of our given for the input to the mechanism. Okay, so we just get 0.6 radians per second. Okay, so 1 radian per second input, 0.67 radians per second output. And you may say, okay, what about the direction? Instance centers, we're actually just going to work with scalar versions of all this. So, these rotation rates, we'll just worry about the absolute value. And to get the direction, clockwise or counterclockwise, we're going to use our intuition, or not intuition. We're going to look at the drawings that we've made. So let's find the direction, clockwise or counterclockwise, of our output. We know the input was clockwise, and that allowed us to put this vector up. Let's look at link 3 and say, okay, we know that point's moving up. So link 3 must also be rotating clockwise. So we're going to use that velocity point, our transfer point, and here we'll find out that it's also turning clockwise. I'll just put my diagram back down here. So we can think about that. Link 2 is rotating clockwise. Link 3 is also going to rotate clockwise. Seems plausible. Okay, so this is your entire process. I'll take 1 or 2 questions now, and then I'm going to write out a general form, a general sort of process with what we just did for any 2 links, I and j. Yeah.
Sorry, could you repeat please the direction part? Could you just repeat it, but just again because I didn't do it.
Yeah, we wanted to find the direction of theta 3 dot. That's the rotation rate of link 3. So we look for a velocity on link 3, and we have one right here. It was the same as P23 up here, and we saw that it was up, so link 3 must be rotating clockwise.
Yeah, okay.
Yeah. So you need to have a diagram like this of your link that you're transferring to, and put that v velocity of your transfer point on there. And you'll be able to quickly see whether it's clockwise or counterclockwise. Yeah, another question? Okay, so the question was to repeat why this one is up. Yeah. So when we were on link 2, let me bring that board down here. When we were on link 2, I was putting velocity of P23 on here. The question is, why is it up instead of down? And that's because we knew from the input, theta 2 dot is clockwise. So link 2 is rotating clockwise, which means all the points should be going this way. So I knew P23 is on link 2 in our sort of thought experiment here, so it had to be up. So just circling around this pivot point P12. Any other questions about this? Okay, so let's write a general version of this expression, of this process that we did. We were talking about links 2 and 3. So this is your headline equation that you can use for velocity analysis using instance centers. So you're going to use some instance center, Pij, to transfer motion between link I and j. And we're going to write the equation. We had equation 1 and 2 over here, 1 and 2. I'm going to write general versions of that. We had, right in this case, I equals 2 j equals 3. That's the case we studied. For any ij, I'm going to write that out here. We're going to find our transfer point, Pij. First, we're going to assume it's on link I. Then we'll do link j next. Okay, so I'm basically replacing 2 with I and 3 with j. Okay, so that's acting like it's on link I, and we'll go through that process. Then you're going to act like it's on link j. So now we're looking at the equation 2 up there, and I'm replacing I with 2, 2 with I, and 3 with j. Okay, so this is our instance center general equation. Just a note, there's an error in the textbook if you refer to that. I think right here, one of these subscripts, there's an error in the textbook. Second edition. First edition I don't think has an error there. I think it wrote P1J here. So this is your general equation. Use it to transfer motion between link I and link j. Or link j and link I. Yeah?
That's E1J, right?
Oh, yeah. Here, I'm making fun of the book, and I made a mistake myself. P1 comma j, because this is link j. So it's the distance between its rotation point, P1j, and our point of interest. Okay, so this may look like a big mess, but once you do 1 or 2 examples of this, you'll see everyone is the same, and you'll be able to write it out without thinking about it after a few examples. For now, you can just memorize that and have it ready to go. Any other questions about our basics? Okay, I'm going to show you a special scenario where things go south. Things don't work out. But we'll be able to handle it. Okay, so what if we have a slider? A link, like link 4, which is not rotating. So theta dot equals 0, meaning there's no rotation of that link. How do we find out how to transfer to that link? For this problem, maybe you're given, your input would be theta 2 dot. And you're trying to find the output, which is the velocity of link 4. That's how we would often think about this slider crank. We'll say point D here on link 4, velocity of the point D. That's what we're trying to find. You may say, we're going to run into trouble. I put I equals 2 and j equals 4. That's what we're transferring to. Right? From our input, link 2, we're going to transfer to our output, link 4. But this theta j dot equals 0. So the whole equation isn't going to mean anything, right? It's all going to be 0. So let's see what happens in a little bit more detail. We would use, for this example, to transfer from 2 to 4, we would use P24. Okay, and I'm going to find that for you. It's right above the pivot point and along link 3. Okay, you could find it using Kennedy's theorem. I think maybe Robin did this one in tutorial, or you can try it on your own. That's our P24 that we can use to transfer. Okay, what else do we need to use this equation? We need the 1, 2, and 1, 4. All right, so we'll say, okay, P1, 2, that's the point about which link 2 rotates. That's here. What about P14? P14 is just a direction, right? It's a slider on a slide. The ground is link 1. So P14 is off at infinity. It's just a direction. So our equation, let me put in everything for this equation. I made one mistake there. It's P1224 and P1424. Okay, so it's the same exact equation, just changing out the subscripts, right? So that's our transference equation. But this theta 4, this is 0. And what is this distance? The distance between 1, 4, off at infinity, and 2, 4, which is here. Right? It's infinity. So here we have infinity times 0, which, that could kind of be anything. So we need another way of thinking about these cases. Anytime we have a slider that's not rotating and it's just translating, we're going to run into this same problem. So our way of handling this is what we always do with instant centers. Let's draw an extended version of our link. And link 4 is the link in question. So we're going to draw an extended version of link 4 that includes our transfer point. And we'll quickly see what's going on here. Okay, so here's link 4. It's got point D on there. Okay, and it's just sliding left or right. And way over here on the left, P24, that's our point of interest. That's up here. P24 is up here somewhere. So just copying just link 4 and our transfer point. So let's extend link 4. Okay, let's extend it to include P24. It's just a way of thinking about, P24 is on link 4 now. And we'd say, okay, if we think about it this way, can we just find the velocity of that? Right? This whole link is translating and not sliding. It's part of link 4. It's only sliding, not translating. So that means for a slider on a slide that's not rotating, so just pure translation, every point has the same velocity. Right, every point on here has the same velocity, and I'll just sketch that as VD here. That's our velocity of interest. Some point here has the same velocity, and our point of interest. P24 has the same velocity. Okay, so sliders turn out to be really easy. Our equation breaks down. We can't use our equation, or we can't calculate the right-hand side of our equation. But the good news is, it's really simple. P24 is our output speed. So instead of writing all this, we can just say, that's our output directly. Velocity of D directly. That's what we wrote here. All these points have the same velocity. VD is the same as velocity of P24. And that's what we've been writing here. That's what these equations are. It's the velocity of P24 equals VD. So forget about doing this. Just calculate this for your input. We know that. And that gives you your output velocity directly. Any questions about that one? Yeah. I assume the direction was right. So you ask about what about the other direction? On this one, that's like if theta 2 was clockwise, it'd be pushing right. You need to figure out the direction, left or right, by some other method. Yeah. Let's just take one more question and then I'll let you go. Yeah.
So sorry, I meant when it's turning to go back the other way, wouldn't there be zero velocity at that point?
That's the limit position, and I'll talk about that next time, about what happens through the whole motion. Thanks, everyone. Have a good weekend.